Okay, so this is lesson on homework 5, which is on the subject of higher derivatives and implicit functions. So let's say we have the function. So this is problem 1. We define the function x goes to exp of sine of x. So this is a composite function, and but it's such a simple function. I just wrote it down like this. I'll do it again in a different way in a moment. So the derivative of f is that, or if you want to see it more, derivative of f of x, just evaluate at x. This is the derivative, and the command to compute a higher derivative of a function is d at n of f. So this is the f derivative of the function f. So for our function, if we want the second derivative, it's d at 2 of f it's that, or if we want to look at it, just evaluate it at x, that's what it is. For the third derivative, we just replace the 2 by a 3. Oops, let me replace it. Yeah, that's the third derivative. For the fourth derivative, we put in the 4. It gets more complicated, but that's the way it is. Now, if we wanted to write this function as a composite function, we could define the function, let's say g, to be equal to x goes to sine of x. Now we could define the function h to be x goes to exp of x. And then the composite function, h composed with h composed with g of x is e evaluated as sine x. So so I could have defined f in terms of as this composite, but this was simple enough, it wasn't necessary. Okay. Problem 2. We have two functions, g and h. G is the function x cubed minus 2 times x plus exp of x. Again, Oops. Let me do this properly. X cubed minus 2 times x plus exp of x. So this is this interesting function. H is the function x goes to sine of x. So the composite function g composed with h of x is this. And if we want the derivative of that, it's that. On the other hand, if we compose the functions in the opposite order, that's h composed with g. That's plugging x cubed minus 2x plus e to the x in for x. And the derivative of h composed with g of x is that. Okay. Problem 3, we have a function, I'll call it f, is x goes to exp of minus x squared. So the derivative of f is that. But we actually want the first 10 derivatives. And instead of writing them all out, or writing the commands one by one, I'll make a loop. For n from 1 to 10 do, I'll put in my n do. And what I want is d at n of f of x. Here are the n derivatives. If I prefix this with an n so I know which one is which. This is the first, this is the seventh, and so forth. These are the n derivatives. Problem 4. We have a function f of x is equal to the sine of 2 times pi times x times the cosine of 2 times pi times x, except it's a 3, so let me change that. So this is my function, and I want to find the tangent lines to the curve at 2 different points. So at x equal 3 pi over 4, I'll call this TL1 for this first tangent line. It is what? It's the derivative of f evaluated at 3 times pi over 8 times x minus 3 times pi over 8 plus the value of the function at 3 times pi over 8. That looks like a mess, but it is the tangent line. And the second tangent line is TL2. Is this evaluated? The tangent line is 7 pi over 8. So we get this horrible looking mess. If we were to plot this f of x, that's what the graph looks like. Kind of complicated. But I'm looking at it, well, okay. And really kind of interesting. But I want to plot this together with the two tangent lines. Tangent line 1, tangent line 2. So it's just to see what's going on slightly. Let me just plot this from maybe 0 to pi. So this is sort of what's going on. And let me just restrict the range of, Okay, so here at 3 pi over 8 is the tangent line. Here at 7 pi over 8 is the tangent line. Let's see, if you want to see where they intersect, I have to go to the left of 0. I'll go maybe minus pi. Oh, they still don't intersect. Minus 3 times pi over 2. Nope. How about 2 pi? Wow. Hard to see where they're going to intersect. Still not. Oh, actually, maybe I didn't get down far enough. Let me make this 50. Ah, so they are intersecting. Okay. So they intersect somewhere down there. You see it on the graph. But to compute the coordinates of the points of intersection, we want to know, solve when does, for what x, does the first tangent line equal the second tangent line. Solve that for x. We get some mess. Let's get it as a number. So I'll use fsolve instead of solve. There we are. And so that's the value of x for which these two lines intersect. And what's the value of y? Let me call this x naught. So that's the value of x as a decimal where these two lines intersect. And if I substitute, SUBS is the command to substitute, x equal x naught into either one of these lines, and if we convert this EV, ALF, this will, in one step, convert it to a decimal, and I'll call this y naught. So that's exactly this point, minus 44. And just to double check this is really correct, if I substitute this x into the equation of the second tangent line, I get almost exactly the same thing. This is just some error in the calculation, rounding errors. That's the coordinates of this point. Problem 5 is to write a loop to solve a sequence of equations. So you just write for n from 1 to 11 do, and do, I always put that in first. And I want to solve the equation x cubed minus 81 times x minus 6 plus n equals 0 for x. And maybe I'll do f solve just to get a simple looking answer. Here they are. When n is 0, this actually has, this is when n is 6. Let me write n comma. So when n is 6, this is x cubed minus 81x equals 0. So the solutions of that are x equals 0 and plus or minus 9. You can see that right away. Problem 6, we want to solve the equation x to the 4th minus 3 times x squared minus 4 equals 0 for x. Seems that even though it's a 4th degree polynomial, it only has 2 solutions. And let's plot this. So that's what it looks like. Look how fast it goes up. I really want to see where it crosses the x-axis. So let me just plot it maybe from x going from minus 4 to 4. Perfect. So now you see it comes down, is 0 at minus 2, comes up, goes down, and then is 0 at 2 again. That's what it looks like. And problem 7 is to plot on the same graph 2 parabolas, x squared minus 7 times x minus 11 and minus x squared plus 13. Isn't that pretty? This is the first parabola going up. This is the second parabola going down. Let me just plot this maybe from There we go. That gives us a better picture, I think. There we go. And we just want to find the places where the two curves intersect. So let's say x1 is the point where the two curves intersect. That means what you get when you f-solve the equation, x squared minus 7x minus 11 equals minus x squared plus 13. Solve that for x. This is minus 2 something. This is 5.6. And the value of y, where they intersect, is what you get when you substitute x equal x1 into either one of these two expressions. Oops, I'm sorry. Let me call this something else. Let me call this A, because you notice there are 2 points of intersection, and what is A1 is the first, and what is A2 is the second. So let's say B1 is A1, B1 are the coordinates of this point. So this is what you get when you substitute x equal to A1 into this. This is about 8.45. Just to see this a little bit better. Suppose I restrict the range of the y. So y goes from maybe minus 30 to 20. So now you can see this point of intersection, it really is this. And if you just want to double check, if you substitute A1 into the second curve, we should get essentially the same thing. Yep. Yep. And what about this point of intersection? Looks like it's about 18 or so. So what we do, we'll call that B2. And we substitute A2 into the curve. And we get minus 18. And just to check, if we substitute B2 into the second curve, we get the same thing. So that is our homework.